Hello and welcome. We have been discussing the effects of quantum mechanics on the gas of electrons in a solid. Typically a metal is what we are considering now. Now, the important thing that we mentioned is that although for transport electrons behaving as a free classical particle kind of theory gave a reasonably good agreement with experiments for thermodynamic quantities like specific heat or heat capacity, the discrepancy between the classical theory and the experimental results was considerable. It is about a factor of 100 or more. Now, the question is where does it come from, such a huge discrepancy, and in one case in transport electronic theory based on classical physics gave us reasonably good results, whereas on the for thermodynamic quantities it did not. So, the discrepancy was actually sorted out when people realized that these electrons are quantum particles and you have to use quantum mechanics, and which came only after 1925. So, the early confusion was sorted out when one started using the Fermi statistics, Fermi Dirac statistics for electron gas and Pauli exclusion principle thereof. Now, again to just recap what I said in the previous class, what we did, we said that the discrepancy is primarily because of the fact that the Boltzmann statistics, for example, velocity distribution runs very high at low temperatures at low energies, and these corrections are these are the things that take care of this huge factor that comes in the specific heat. Look at the Fermi Dirac distribution, which is cut off by 1, it is always 1 here, and it has a small almost vertical drop at around kF or energy EF. Whereas the Maxwell-Boltzmann distribution is very large at very low energies, and then it falls off exponentially. So, the low energy specific heat will using Maxwell-Boltzmann statistics is going to be wrong. It is going to be off by a factor of 100 or more. The other interesting thing is that this classical statistics will not give you a linear in temperature dependence, which I said is what people found at low temperatures for a gas of electrons. When the ionic contributions are negligible, you only have electronic contributions to specific heat, and at that point at low temperatures you should experimentally people found out that it is linear in temperature. So, that linear in temperature dependence will never come out of classical theory, because classical theory gives you just a constant, it is independent of temperature. Now, when you apply quantum theory, you have to be alerted by the fact that the Fermi Dirac distribution has a form which is at 0 temperature, it is just a box kind of structure. It goes all the way up to a particular energy and then drops off vertically, and as temperature rises, that vertical drop off sort of becomes smeared, and it is the drop becomes less vertical, it has this finite slope and so on. But it is interesting that if you just look at this nature of this function, at E equal to EF, it will always pass through half. But now what will happen at finite temperature is that some states from here will be lost, and they will come beyond the EF. This is shown at different temperatures, for example, in this graph. And that is what causes the specific heat of a degenerate electron gas. that there are excited states beyond the EF at finite energies, finite temperatures. So, and one another thing I mentioned is that the at very large energies, of course, the Boltzmann statistics and Fermi energy and the Fermi Dirac statistics almost merge, which is very clear from this expression. When the exponent dominant, exponential factor dominates, you can neglect the one and then you get back your Boltzmann statistics. Now, this is what we argued, that if you have a so let me just give a recap of the argument. The electronic states are filled up to, say, suppose these are your electronic states as shown in this picture. These are the states, all of them are filled up to a certain energy. So that energy is EF. Now, as I said, if you now want to give supply some heat energy to this system, suppose all of these are filled up to at 0 temperature, just filled up to all these are filled up to Fermi energy, and you are supplying an energy kBT. Now, the point is that suppose this is the kBT. This is the kBT amount of energy that you are supplying. This is my energy axis. So, how many electrons can take the energy? The electron which is here, if one gives it kBT amount of energy, this electron, for example, will rise up to probably here, but there are no states here. So, these are all these are states where this electron just cannot go. I cannot take it up here because these states are all filled up. So, the only electrons that I can take out are within the distance of kBT. They can accept this energy to get excited, and they will be excited beyond EF. So, this electron, for example, can go here. So, if this kBT is slightly more than this distance, this energy difference. So, the electrons which can go, these are, so up to this is forbidden basically. You cannot excite, and only ones which are excited are within kBT. So, they are the ones which can accept the energy kBT. Now, how many of them are there? I mean, typically the number of states here is G at EF, G at EF, the density of states, which is almost, I can write it as 1 over EF proportional to. Now, remember it is 3 by 2 n by EF. So, it is inversely proportional to EF in the free electron theory. So, the number of electrons that takes this energy is proportional to kBT by EF, right, this ratio of these two energies. So, this is all the way from here to out of all these states which is EF, a fraction of states which is kBT by EF, these number of states can accept the this energy. And how much energy can they accept? They will each accept kBT. So, electrons lying within this range of this fraction of total electrons, this fraction of total electrons will take that energy, and how much energy each takes? This is the energy. So, it is proportional to T square, kB square into T square. Now, this is, if this is the energy change in energy, then of course, the derivative with respect to temperature will give you a kB square into T factor divided by EF. Now, this division by EF, this denominator, is extremely important, because remember we needed a factor of 100 or more, and if you look at the temperature, typical temperatures are say 300 degree Kelvin, and typical EF is like 50,000 degree Kelvin, right. So, so this immediately gives me this huge factor of more than 100 to 500 and so on. So, that basically resolves this problem of finding a specific heat which is linear in temperature first of all. So, this linearity and the factor that T by kBT by EF. So, this I can write as into kb. So, this factor gives me the the 100 that I was looking for, we were looking for to match experiments. Okay. So, both the problems are resolved by this argument of Pauli, using Pauli principle, that means quantum statistics. So, one can make it more formal, and that is what I am going to do now. So, let us just do a treatment which is somewhat more formal than what I have just said in words. Okay. So, the energy E is basically, as I said in the previous day, that I can convert the K integral into an energy integral using the density of states G E, then E dE 0 to infinity. Okay. So, this is my energy of the system, but then this is not exactly correct, because at finite temperature you have to multiply this by the Fermi function. So, this is the energy of the system. Similarly, the total number of particles is of course again 0 to infinity G E F E d E. Okay. So, these are the two equations that I am going to use. So, at 0 temperature, for example, the E at t equal to 0 is basically the same integral, but there are two things are important, that F E, remember that F E is just 1 at 0 temperature, this is 1 F E versus E. So, this integral at 0 temperature will become from 0 to E f, because the F E is 0 beyond that, epsilon G epsilon d. Okay. So, this subtraction of this from this will give me the change in energy at a finite temperature. So, it is E. So, it's epsilon G E F E d E 0 to infinity minus epsilon G E d E 0 to E f. So, that is the change in energy at a finite temperature. So, let us just also write the n equation, which is so that equation is already here. So, I will I will use these two equations. Okay. Now, what I need is basically a so what I do is that I do two things, del E by del T, that is equal to epsilon G E del F del T d E 0 to infinity. Okay. So, this is see, because the other terms are constant in temperature. So, they fall off, they are just they cancel out. So, I do not have to bother about those terms. So, this is basically my electronic specific heat, C electron. Let me write it. C electronic is this. Now, I multiply that previous equation for n by E f. So, E f into n equal to just E f into to infinity G E d E into F E. Okay. Now, this left hand side both these are constant numbers. So, if I take a derivative with respect to t, this will just give me 0. So, this will be 0 E f f del t G E d E. Okay. So, if I now subtract this one from this one, then what I will get is C electronic equal to E minus E f G E del f del t d E, right. Zero to infinity. Now, this is so far we have not done any approximations, but this is the point where we can make some approximations, and the level of approximation tells you at what degree of correctness you will get your results. For example, the Fermi function, as I said, is like a box like function. There is a vertical drop here at 0 temperature, T equal to 0. So, if you take a derivative of Fermi function, then you will get 0 all the way from here, from here to here you will get 0, but except at this point E f, where you will get a value, because it drops, it is like a discontinuity at this point. So, you will get a function which is the derivative function will be like this. So, it is like a delta function in the negative direction. So, this minus del f del t is actually a delta, behaves like a delta function at 0 temperature, but the moment you deviate from 0 temperature, of course, this delta function picture will not work, but you have to then take the exact derivative of the Fermi function, and then of course, you have to, the calculation cannot be done. See, if you do the calculation using the Fermi function, then you have to do the whole calculation, in the sense you have to integrate the equation, and that integration is not easy to do. Nevertheless, what one can make some kind of an approximation is that you assume that your G of E, which is which in 3 dimension, for example, goes as e to the power half, and in 2 dimension goes as e to the power 0. You can assume that this the regime of energies that we are talking about is about around E f. There is a small energy range, 1/100th or even less than the value of EF of with kBT. So, within that range of temperatures we can assume that the G of F can be replaced by its value at the Fermi level. So, if you do that, then of course, your C of electronic is you can pull it out. The G of EF can be pulled out of the integral, and then the rest of the integral remains dE E minus EF just a second. D of E minus EF, then del F del T. So, this integral has to be evaluated. Now, this of course, you can calculate del F del T, because you know the F as a function of temperature also. So, all that can be done, and you can put those values in, and if you do that, an approximate calculation leads to the value which is about 1/3 pi square GEF into kb square T. So, this is kind of a back of the envelope calculation valid up to the order, more or less valid up to the order T. It does not take care of the shift of chemical potential, change of chemical potential due to the thermal effects, because we are working at finite temperatures. We should have used that, but this approximation still gives us the linear in T dependence and the factor 1/3 pi square. Now, if you remember, G of EF for a free electron gas was 3/2 N by EF, then your C of electron in this theory is 1/3 pi square, G of EF is 3/2 N by EF into kb square into T. So, these 3 cancels, it will be half pi square equal to, this will give me half pi square N kb square T by EF. So, this kb square T I can write as kb T into kb. So, I put a kb here, N, then a kb here. Now, look at this, this is pi square so half pi square into N kBT by F. Remember, it was 3/2 N kb only in the classical theory. Here you have a factor kBT by EF and a numerical factor of about 1/3 to that. So, so this factor kBT by EF gives you a factor of 100 or even less, and the linear in temperature dependence comes out of this kind of a back of the envelope calculation. I mean, it is a very simple approximate calculation. One can even do better. I mean, that is the whole exercise that Sommerfeld took. What he did was that he wanted to correct this calculation. He wanted to make, first of all, write down a general calculation where this kind of integrals appear, where you have to sum over the degenerate states and their energies and so on to get physical quantities. So far what we have done actually pulls out the physics correctly. Remember, the physics involved 2 things. We required a factor of about 100 less than the classical value, which this one is, right. So, So, if you compare this one for example with 3 by 2 n kb, then you can see that you are only a factor of 1/3 pi, you are down by a factor of pi square kbt by EF. So, that kbt by EF gives me a factor of 100 less than the this. See, 1/3 pi square is like 3 or something close to 3. So, that is not important, a factor of 3 would be alright, but there is this factor of 100, and this factor of 100 1 by 100 gives me the correct ballpark figures for the specific heat. Besides, it also gives this very important factor that the specific heat of electrons which is visible at very low temperatures when ionic specific heat is already down, and this specific heat, electronic specific heat for a gas of electrons in a metal is proportional to temperature. So, these are the two major achievements of this kind, this particular calculation, which was first undertook by Fermi, and it's, as you can see, it's a simple back of the envelope calculation, approximate calculation gives you the correct result to order T. The question of course is, can I do better than that, and that involves the so called Sommerfeld corrections. Sommerfeld did these calculations correct up to order T square. Now, that calculation I will just show briefly as to how to do it. It is not to be remembered, and it is it's a fairly complicated long calculation, and if you ever need corrections up to order T square, then of course you have to look at these calculations. So, as I said, the main corrections will come from the change in chemical potential. So, let us see what Sommerfeld did. Okay. So, this is what we will start right now. Thank you.